everybody. Thanks very much for coming. This morning I'm going to be talking about oddities from the Tsumeb mine, and those would be pseudomorphs, casts, coatings, phantoms, and oriented deposits. So we're going to be looking at a lot of beautiful and fascinating specimens like these, but you know how a long time ago you were told you can't have dessert until you've eaten all your vegetables? Well, we can't look at any of these pretty pictures before we go through some terminology and classification. So pseudomorph, of course, is Greek for false form, and the classifications of pseudomorphs is something that has been discussed a great deal through the years, and there was an article just published written by Cyan Fraser, which is a wonderful, rigorous examination of the different types of pseudomorphs, and I recommend this highly. It shows how complex the field of pseudomorphs is, but I am going to use an abbreviated and simplified version of their classification for simplicity and to allow us to have more time to look at nice pictures. So the first type of pseudomorph that I'll be talking about is the chemical alteration type. And this is the type where the original crystal shape is retained, but the chemical composition of the mineral is different than it was when it was first formed. So sometimes it's very easy to identify what the original mineral was based on retained morphology and the simple chemical change. And a good example of that is azurite pseudomorphed to malachite. However, in other cases, it may not be nearly as obvious what the morphology of the original crystal and the chemistry was. The second type of pseudomorph I'm going to talk about is a paramorph. So this is where the pseudomorph has the same chemical composition, but the crystal lattice is different. And a good example of this is argentite, which forms at very high temperatures, but as soon as the temperature drops below approximately 350 degrees Fahrenheit, argentite, which is isometric silver sulfide, transforms to acanthite, which is monoclinic silver sulfide. I am not going to be showing any pictures of acanthite from Tsumeb because there aren't really specimen quality or display quality specimens. They're really only tiny specks. The next type of pseudomorph I'll be covering is encrustations, or a simpler word, coating. And it's a coating with the original mineral remaining underneath the coating. Now, this is also known as a perimorph, but I'm going to avoid saying the word perimorph because it sounds very much like item number 2, paramorph. So I will just be calling these encrustations or coatings. The fourth type is an epimorph, or more simply, a cast. Here, the coating of the original crystal is present, but the original mineral is gone, so that is a cast. Unfortunately, there's another meaning for the term cast, and this is where a new mineral fills the hollow of an epimorph, making a cast in a mold, and this is like the lost wax casting method. So you start out with a wax model. Here the wax model is encased in plaster. Then the wax is melted out, leaving an empty plaster cast. Then you pour some molten metal into the plaster mold. You break the plaster mold, and you are left with the metal cast. So cast has two words. There are two meanings that are contradictory. It can be a hollowed out epimorph. It can also be a solid shape produced from casting in a hollowed out mold. In the mineral collecting community, however, a cast usually refers to a hollowed out epimorph, and that's the usage that I'll be relying on in this talk. So originally the slide only had 5 types of pseudomorphs, but there really is a 6th type that is very important, and that is one where there are complex combinations or overlaps of the above 5 processes. And you can actually see a spectrum of different processes involving the same combination of minerals in different specimens, and I'll have a good example of that a little later on in the talk. So now, let's start talking about pseudomorphs by talking about chemical alteration pseudomorphs, and this really is what most people think of when they think of pseudomorphs. And the first mineral to be pseudomorph that I'm going to talk about from Tsumeb is azurite, and azurite was very plentiful at the Tsumeb mine, and there are many different pseudomorphs of azurite that can occur. The first one is azurite to malachite, and Wendell Wilson has dubbed this the king of pseudomorphs. I think that's a very good name for this type of pseudomorph because malachite pseudomorphs after azurite are really wonderful specimens coming from so many different mineral deposits around the world. Another reason this is a good one to start with is because the chemistry of this pseudomorph is actually quite simple. You just take some azurite and you mix it with a little water, and given time and proper temperature and pressure, this is transformed to malachite and also carbon dioxide. So a very simple chemical transformation. And here are some examples of malachite after azurite pseudomorphs. Here's a lovely crystal where the top part has been pseudomorphed, but the azurite remains on the bottom part of the pseudomorph. Here we have 2 specimens where the entire specimen has been transformed from azurite to malachite. This one has a somewhat mottled and irregular surface, whereas this one has a very interesting pattern on the surface, a bunch of concentric circles, sort of like the rings of a tree, and this really demonstrates the way that this pseudomorph formed in all likelihood with little spots of transformation from azurite to malachite, starting in the center, and then the transformation gradually radiating out until the entire piece was transformed to malachite. Now, azurite from Tsumeb has numerous different morphologies, and for this reason you can see malachite after azurite pseudomorphs also in a very wide variety of wonderful morphologies. Here's another blocky blade-like crystal with some smithsonite on it. And here's a particularly interesting pseudomorph of azurite after malachite. And you can see this V-like configuration is actually a twin. Now, of course, it wasn't the malachite that twinned, it was the azurite that originally formed in a twin and was then pseudomorphed. Here's another fascinating specimen where you have a lustrous and blade-like crystal of azurite that has been partially encased by coarse bundles of malachite needles. So sometimes the malachite does not stay malachite. Sometimes it is transformed further into rosacite. And this also has a relatively simple chemistry where you take some malachite and you give it some zinc ions, and what you get is rosacite, and you get copper ions that are released. And these are very popular specimens, quite beautiful, variable in color from dark blue to a lighter blue. Here are some other examples, and in these examples you can see that often these double pseudomorphs are not completely transformed to rosacite. You can see a little malachite here at the base, and in this specimen you can see that there is a relatively thin layer of rosacite that has flaked off the malachite underneath. The bright green periphery of this specimen is arsine tsumebite. Here's another very interesting rosacite. In this one, it has a very marbled appearance, and it also has a sprinkling of a second generation of azurite crystals on the surface. In this one, it's fascinating because part of it has been transformed to rosacite, but the other part of the specimen remains malachite. And perhaps the reason for this is that the initial pseudomorph was just this portion, and after the malachite was transformed to rosacite, perhaps a second generation of azurite crystallized, and that was later pseudomorphed to malachite. Here's a pair of pseudomorphs where the malachite has been coated with a thin coating of druzy quartz, quite lovely and sparkly. So here are some other things that will end up after a azurite has been pseudomorphed. Here we have some examples of smithsonite after azurite, and I'll call attention to these little yellow prismatic crystals on the surface. These are mimetite, and the reason that I point these out is that these little mimetite crystals are also found on other pseudomorphs of azurite. These are willemite pseudomorphs, and again, you can see the little mimetite on the surface. These willemite pseudomorphs after azurite sometimes are solid, but other times they are hollow, as in this case. And when they are hollow and you see inside, you can see this bubbly botryoidal formation of willemite. Here's a lovely bright green pseudomorph of baeldenite after azurite. Here is brochantite after azurite. And here's an example where the azurite has been pseudomorphed to tennantite. So azurite can go in many different directions at Tsumeb. So now talking about what happens to tennantite. Here we have another pseudomorph, and in this case, the tennantite is thought to have formed from chalcocite. This determination is somewhat uncertain, but because of the twinning apparent in many parts of this specimen, it is thought that it started out as chalcocite. Here's another interesting tennantite specimen. In this case, we see hexagonal barrel-shaped crystals, and so this suggests that this mineral specimen started out as mimetite that was pseudomorphed to tennantite. Here, the morphology with the flat pinacoid and the sort of lenticular cross-section is suggestive of an argite after tennantite, or tennantite after an argite. Now we'll talk about cerussite pseudomorphs. Here's a very popular category of pseudomorphs where the cerussite has been pseudomorphed to mimetite, and we can see this in all different crystal forms of the cerussite, so there's a wide variety of shapes that can be seen with this pseudomorph. Here we have some wonderful examples of cerussite pseudomorphed to hydrocerussite. This one is a specimen of willemite after cerussite, and it may be a little bit challenging to recognize this as cerussite. Well, my pointer is not working, sorry. But in this area here, you can see a hexagonal form, as well as some cyclical twins, which is consistent with cerussite. Here's a very interesting specimen. This is duftite and calcite after cerussite. Now, anglesite pseudomorphs. Here is a hydrocerussite after anglesite. And here is a large blade of anglesite that has been pseudomorphed to colorless crystals of cerussite. So now, mimetite pseudomorphs. These are particularly colorful and beautiful. The arsen tsumebite and beldenite both can replace mimetite. Often both species will be present in one specimen. And again, with so many different shapes of mimetite, one can see a wide variety of different shapes of these pseudomorphs. Here are two more examples of beldenite after mimetite, and the item on the right, you can see the typical prismatic crystals with flat pinacoidal terminations. Here you have a hexagonal prism, but there are pyramidal terminations. So now, copper and cuprite. Here we have an example of malachite pseudomorph, malachite after cuprite, similar to the specimens that we know well from Bongania and from Chessy. Here's something a little different. What we see here is that cuprite has been pseudomorphed to native copper. The specimen on the left, you can see that there are octahedral faces in these two locations, and here we see dodecahedral faces, so the combination of the tetrahedral and dodecahedral crystal faces really indicates that this started out as a cuprite. The specimen on the right has these small rounded pseudomorphs of copper after cuprite, as well as native copper, primary native copper in arborescent crystal form. Here's a pseudomorph that's gone in the opposite direction. It started out as native copper in arborescent crystals, and it was pseudomorphed to lustrous cuprite. Here we have native copper that has been pseudomorphed to malachite on a matrix of mimetite crystals. And here we have native copper that has been pseudomorphed to matramite, surrounded by a matrix of calcite crystals. So I've shown this picture before, and this is just some chalcocite pseudomorphs. So we have chalcocite here, which is pseudomorphed to tennantite. And here is an illustration from Gebhard's book that shows a pseudomorph of ludlokite after chalcocite. Here is what was once a crystal of galena that has been replaced by chalcocite. The face here is somewhat concave, and the reason for that is that the size of the chalcocite crystal or crystal lattice is smaller than galena, so the overall specimen has shrunken somewhat. Now, tennantite pseudomorphs. Here is a lovely specimen of dolomite after tennantite. and tarnowitzite. There are many different species that can replace tarnowitzite. Here is calcite after tarnowitzite. Here is dolomite after tarnowitzite. Here is smithsonite after tarnowitzite from the small, well-known find from 1929. Here is a dolomite after calcite, a lovely specimen, well-known. Now we're going to talk about casts, or epimorphs. This is a cast that many of us have possessed at one time or another, gypsum after Homo sapiens. And as is often the case in the mineral world, there are some specimens that are more aesthetic than others. So dolomite casts, this is a category in itself. There is a wide variety of different dolomite casts that can be seen. Here on the left side, one can see what is the front of the specimen with rounded surface of dolomite crystals, orange to yellow in color. On the right side, we can see the sharp recesses where the calcite crystals used to be, and those recesses have been partially filled with small duftite and calcite crystals. Here we have a snow white dolomite cast. We can see the very sharp imprints of the rhombohedral crystal forms. On the front side of the cast, there is a sprinkling of malachite needles. And these casts come in many different colors. The one on the left is colored by cobalt. The one in the middle, where one sees the sharp rhombohedral outline, is presumably colored by copper, and the one on the right is colored by iron oxides. Here we have a dolomite cast after tarnowitzite. You can see the very characteristic shape of the tarnowitzite crystals, and looking underneath, you can see that that the specimen is hollow. Here's an interesting dolomite cast, this time after cerussite. Here is a siderite cast after calcite. And here we see the sharp rhombohedral form of the calcite crystals, but this has been replaced by smithsonite. On the left, we see another smithsonite cast after calcite. The piece on the right, it's a bit harder to figure out what exactly was present before these hollow spherical forms of smithsonite formed, but perhaps they were spherical aggregates of calcite crystals. Here is another unusual species, calcioduftite, that has formed on top of a plate of rhombohedral calcite crystals. And here is a cast of malachite. Again, after calcite, you can see the outline of the rhombohedral crystals quite clearly in this lovely specimen. Here is mimetite cast after cerussite, similar to the solid replacement pseudomorph that I showed earlier. You can see the typical cyclical twinning of cerussite on the top side of the specimen, but underneath it is hollow, filled with small needle-like crystals. This is a cast of hedithane after mimetite. You can see all these little tubular structures. They are hollow in the center. And And so that's where the mimetite was before it was encrusted with the hetiphane, and then the mimetite dissolved away. Here is duftite after wolfenite, and you can see in the close-up picture that where you have broken crystals, they're empty. There is no residual wolfenite inside. Here is another example of matramite cast after wolfenite, and again in the few areas where there are broken crystals, you can see that it's empty. So no wolfenite remains. So now let's talk about coatings or encrustations. Here we have a sample of druzy quartz with the wolfenite still present within the druzy quartz. Here is goethite encrustation on wolfenite, and on the close-up view, one can see that there still is a little wolfenite present inside the goethite. Another lovely specimen of dolomite after wolfenite, and here's still another lovely specimen of dolomite after wolfenite, and again one can see the wolfenite is still present inside of the dolomite coating. Here's a thick incrustation of matramite on calcite. You can see that the overall specimen has the appearance of rhombohedral crystals in a subparallel arrangement, and on the left side one can see the point of one rhombohedron of calcite peeking out from the back of the specimen. Here we have duftite encrustation on calcite, and here we have aragonite on calcite. These specimens are thought to be formed post-mining. In other words, water from the surface flowed down through the mine and along the way picked up calcium and carbonate and some copper ions as well, and this was all deposited on top of the calcite rhombs with the aragonite taking a blue color from the copper ions that are present. Here's a lovely encrustation. We have a malachite after azurite pseudomorph, and this in turn has been coated with a thick layer of green smithsonite. Here smithsonite is coating crystals of tennantite. And here's another example of smithsonite coating tennantite. One other very notable thing about this wonderful specimen is that it is a twin crystal of tennantite. You can see the twinning right there. And this next specimen also is a twin crystal of tennantite. However, this one has been coated by malachite. In this case, the tennantite has been coated with mimetite crystals. In person, these specimens are extraordinarily sparkly and lovely. And here, the tennantite has been encased in wolfenite. This specimen has multiple species on the tennantite crystal. The Tsumeb is the tan or orange colored crystals in this part. The duftite is the green up top, and the yellow, more finely crystallized area is the gartrolite. Here's an unusual specimen from Tsumeb, pyrite. Pyrite is thought to be quite uncommon in Tsumeb, but this is a known discovery there with several specimens that I have seen with quite euhedral pyrite crystals that in turn have been encrusted with galena. On the back of this specimen, the There are places where the galena has chipped away, revealing the brassy pyrite underneath. Here are two specimens of calcite that have been coated with druzy quartz. The one on the left has been colored by malachite inclusions. The one on the right has been colored by inclusions of chalcotrichite. Here's a specimen of duftite that has been encrusted with druzy quartz. And here's a wonderful specimen of arsine tsumebite coating anglicite. And there are a few small areas where the coating has broken away. And you can see the clear, colorless anglicite underneath. So now let's look at cerussite and the various things that it can be coated with. Here we see a lovely example of cyclically twinned cerussite that has been partially coated with green rice grain shaped crystals of cerussite. Here's another example where the smithsonite consists of tan rhombohedral crystals. Another interesting thing about this piece is that there is some native copper on the backside. And pink smithsonite even gets into the act coating cerussite in some cases. Here is cerussite that has been coated with arsine tsumebite. And here is a cluster of of cerussite crystals that have been encrusted with a thick coating of needles of malachite. Here the cerussite has been coated with dolomite, and here goethite is coating a crystal of cerussite. Here is a very striking specimen that I saw at the Colorado School of Mines Museum, where there is cerussite, and the whole specimen has been coated with the rare species odovite, cadmium carbonate. Quite a wonderful example. Speaking of wonderful examples, here is a very striking cerussite cluster that has been coated with dioptase. And here is mimetite that is coating cerussite. And if you've heard me mention mimetite and cerussite before, I have. And this is really a very interesting set of pictures where one can see that mimetite can be connected with cerussite in several different ways. It can be an encrustation, it can be an epimorph or cast, and it can be a solid, complete replacement. Based on this, I would say that mimetite and cerussite have a very intense and complicated relationship. So next we're going to be talking about phantoms, and don't worry, these are not the scary type of phantoms, these are nice phantoms. Here are two examples of phantoms. The crystal on the left is clear, but at various points. The crystal had deposition of gray matter, and as a result of this, we see many different terminations that formed in the process of the crystallization of this prism of cerussite. The example on the right, there was malachite deposited on the cerussite, and then the cerussite resumed growing with a clear colorless cerussite on top of the malachite. Here we have a very interesting example of a phantom from Tsumeb we have hematite and duftite as phantoms in calcite. And you can see that there are these triangular shapes. The green part is duftite and the reddish-brown part is hematite. And the question is, how did it form like this? And to answer this question, it's worthwhile to look at some basic crystals of calcite. And of course, this is the rhombohedral form, and this is the scalenohedral form. And even though these are very different crystal shapes, they have the same underlying crystal lattice. It's just that certain crystal faces formed faster than others. And in fact, one can superimpose the rhombohedron on the scalenohedron in a way that aligns the crystal lattice. This is important because this phenomenon is actually going on in the specimen that I just showed you. As we can see in the diagram here, we first had a scalenohedron of calcite form, and then the duftite was deposited on the termination, and the hematite was deposited on the other side of the termination. And then after those deposits were made, the calcite resumed growing, but not in a scalenohedral habit, but rather a rhombohedral habit. And you can see here that the rhombohedra are positioned at the apices of several scalenohedral crystals. And that's how this lovely phantom specimen developed. Now that we've seen that, we can see the same sort of process occurring in this specimen where it was just hematite that colored the scalenohedral crystals before a second generation of calcite grew that was colorless in the area of the scalenohedral termination, but opaque in the peripheral parts of the rhombohedron. And this will be an important observation that I'll refer back to in a few slides. This is a very nice illustration from Syncancus that just shows how phantoms can develop as a result of different crystal faces growing faster than others. In other cases, we can have preferential growth on selective crystal faces. I'm not sure exactly how this developed, but I think what happened is that there was directional flow in the pocket, and that led to the granular crystals being deposited on all the faces that were facing down this way, and then a second generation of calcite formed on the crystals that are facing upwards. And this was a clear and relatively colorless crystal face. Now we see another phantom, and here we have the phantom that basically is parts of the rhombohedron are opaque and parts of the rhombohedral faces are transparent. And I call your attention especially to this item right here where we're looking down onto the rhombohedral faces and we see a sort of a Y-shaped configuration. At least if you use your imagination, you can convince yourself that there is a Y-shaped configuration there. And the reason that that Y-shaped configuration is important is because it is useful in explaining selective deposition. Now, what do I mean by selective deposition? Well, here we have the Mercedes-Benz calcite with the duftite oriented on the faces of the rhombohedron. It looks almost like the green has been spray painted onto these parts of the rhombohedron, but in fact, if one sees this piece in person, one can see that this calcite is opaque, but the calcite here is entirely transparent, and one can see the duftite through the transparent calcite. The other thing that is worth noting about this specimen is that these rhombohedral faces are not entirely complete and intact. There are little defects at the apex of the rhombohedron where the calcite is missing. And we'll see other pieces like this in just a moment. So here we see another example of duftite that is zoned on the rhombohedral terminations, and a close-up picture really helps explain what's going on here. We look at the crystal here, and the prism faces of the calcite have been coated with duftite, but then what you have is a second generation of calcite at the apex of the crystal, which is forming a kind of a scepter shape. But the scepter head is not completely formed. There are gaps between each of these three plates that are forming the scepter head of the crystal. And as these plates do not quite join, they're incomplete, one can see the beginning of this Y-shaped configuration of the Mercedes-Benz calcite. Here we see a different type of deposition of duftite on calcite, and here it really appears that the duftite is deposited only on the terminations of these prismatic crystals. And though one might think that this could be due to directional flow through the pocket during the formation, if you look at the specimen on the right, you can see that the prismatic crystals are really facing in every direction, and only the terminations are coated with the duftite. So it really does look like it's due to epitaxy rather than just directional flow in the pocket. Here we have another fascinating specimen, and in this case what we see is that the duftite has been deposited on the termination of the prism, and then we have a second generation of growth, but it is not covering the entire termination. There's a very sharp edge here where the duftite is still visible. And as this second generation of calcite has formed, it also forms this Y-shaped Mercedes-Benz pattern. And for good measure, this specimen has not only duftite in this pattern, but also fine deposits of dioptase. Here we have one that I haven't been able to figure out. We have a simple rhombohedron of calcite, and initially, I suppose, just the entire rhombohedron was covered here, and then there was a second generation of growth that extended out, with the result that only 1/4 of the rhombohedron of duftite was coated with 1/4 of the rhombohedron of calcite was coated with duftite. Lastly, here's a fascinating specimen that I recently saw on social media of smithsonite as the matrix with calcite crystals with the corners of the calcite crystals colored by hematite in, again, what appears to be an epitaxial pattern. Really fascinating piece, and evidence that there's always something new to see in Tsumeb, and it always has new fascinating questions that we have to approach. But what's really striking about all of these combinations of different minerals is that the complexity of the Tsumeb mine is really extraordinary, leading to all these extraordinary combinations of different mineral species in very aesthetic and appealing patterns. So these are just my acknowledgments for all the people who helped me put together this talk, providing specimens and photographs of specimens, and I thank them very much. And I thank you for your attention. Any questions?